In this video, we're going to learn how to take the information from our refined model and use it to make a prediction on unseen data. So in the video before this, we assessed the output of the model. We made sure that our coefficients made sense. We made sure that our p-values were less than 0.05. And then we compared the models from the baseline model to the full model to the refined model to see the improvements we were making in not only the model statistics, but also the underlying assumptions of equal variance and normality. Now, we could go through another round of refinement, but we also have to find a balance between overcorrecting the data to fit the sample and a model that generalizes well to the population. So we're going to move forward with the model that we have here. And to begin, we're going to add a new worksheet called Model Prediction Lab. So I'm just going to click on this plus sign down here, and then Model Prediction Lab. Okay, now in your lab PowerPoint, there's a table on the Model Prediction Lab worksheet that has the test case data. Before we get that test, actually, let's go ahead and get the test case data, and then we'll get our model coefficients to go along with it. So if we go to our PowerPoint, we're going to use this data to make a prediction. So remember, this is our prediction equation here. Okay, and this, again, this final model is just a mathematical equation. It takes a series of inputs, so those are the x values in my prediction equation, and it multiplies them by these beta coefficients, the B1, B2, B3, B4, and these have been estimated by the model to minimize the residual values. And ultimately, when we solve this equation with all of our beta coefficients and model inputs, then this y hat will give us a prediction value. So in the real world, we would build our model with a sample of training data and then validate how well it performs with a sample of test data. So when solving this prediction equation, again, we need to make sure that our inputs are transformed or used in the same way that they were used to build the model. And then also, if our target variable, in our case sale price, was transformed to build the model, then we need to reverse that transformation to convert it back to the original value in US dollars. So for example, we're using cube root of sale price to build the model. We'll need to cube that model result to convert it back to sale price. Okay, so over here I have the beta coefficients. These come from the model table in your regression output. These are three original test cased data observations. So it has the fireplace, the borough, the overall quality living area, and the sale price. And to the right, we have the transformed versions. So fireplaces we didn't transform, it remained in its original form. Our nominal variable we had to dummy code into ones and zeros. So for this first one in the Crawford neighborhood, we see a 1 for Crawford and a 0 for the other values. Second one was in the Brookside, so that's our reference category, which is why we see zeros across here for our inputs. And North Ames has a 1 in North Ames and a 0 for the remaining boroughs. We also have our overall quality rank, where 1 was below average, 2 was typical average, 3 was above average, 4 was good, 5 was very good, and 6 was excellent. So we have our ranked version here, and then we have our square root of sale price here. And then we have our actual sale price values, and then our cube root of sale price value, which is what we use to build the model. Okay, you can actually copy this table right here specifically from the slides, Control C or Command C to copy, and then when you get back to this part of your Excel workbook, you can paste it here. Okay, so you have those values ready to use. Okay. All right, so I'm going to go back to the PowerPoint just for a second so we can review the next slide. So ultimately, this is what we're going to do. So this is how the model equation is built. So remember, this y hat is our predicted sale price. It will come out as a cube root prediction because that's how it was input into the model. Beta 0 is our intercept value right here, 32.28. Beta 1 is this beta coefficient associated with fireplaces, and then we multiply that by fireplaces. Then we add beta 2, okay, the coefficient for Crawford dummy, and multiply that by the Crawford dummy. Beta 3, our North Ames dummy, 3.2, we insert that into the equation and multiply it by that North Ames dummy input, so on and so forth. So that's how this model equation is built. These beta coefficients are estimated in your model table output, and then you multiply them by these transformed test case values to get a prediction. So this is just an example of what it would look like to do it by hand for test case 1, this very first one here. But we're actually going to use Excel to do the math for us. It'll just make our lives a little bit easier. So you can see here are the 3 prediction test cases. You can see with this first prediction case, we were able to predict it within $222. This second prediction case, the actual value was about $9,000 more than we predicted it should be based on other houses that were similar to it. And this last test case was an under prediction of almost $7,000 based on other data that fit this similar criteria. So just remember, in the real world, we don't get perfect predictions, and our model is built to predict the most likely case. So this could be an indication that this house was, they got more money for it than it was worth, or there was some other feature of this house that has not been accounted for that made that difference. And the same thing here. So, but all of these predictions are relatively close to what the actual value is, and maybe in this case, they could have listed the house for a little bit more money, or again, there might be some other factors that we're not considering that might be the reason for the difference in that prediction. So I'm going to go back to Excel, and then we're going to do this together. Okay, so back to Excel. Okay, so now the next thing that we need to do is we need to get these coefficients from our model table in our refined model lab. So you have to have built that refined model in order to get these estimated coefficients. So I'm going to copy that, and then we'll paste these values here. Okay, so we'll just expand that so we can actually see the values. So again, this is beta coefficient B0, this is B1, B2, B3, B4, B5, B6, and B7 in that model equation. So right here, B0, B1, B2, B3, B4, B5, B6. So those coefficients are what are input for those beta values here in your model equation. Okay, now to do test case 1, so this intercept value, if you look at the equation, it's not actually multiplied by anything. So if we multiply it by 1, then it will remain the same, right? I think we can all agree if we multiply 32.28 times 1, then that would also equal 32.28. So it would remain its original value. So that's why you'll see here it is being multiplied by a value of 1 in each of these prediction assessments. So for this X input for our intercept, we're just going to put a value of 1. Okay, now the rest of them can come from right here. Okay, these are the X inputs. This is X1, there was one fireplace for this house. X2, this is in the Crawford neighborhood. X3, 4, and 5 just means that they were not in those neighborhoods. X6 means that it had an overall quality rank of 4. which I believe is the above average category. And then x7 is the square root of living area. So I'm just going to copy these. So just highlight this green row right here, Control C to copy, and then I'll transpose paste it right underneath this one that we entered, because the first value is the input value for fireplaces. So if I click in this cell right next to the fireplace coefficient, right click and select transpose paste, then it will paste those X inputs right next to it. Okay, now the next thing that we're going to have to do is the multiplication. So if you look at the model equation, okay, we can see we're multiplying these beta coefficients by the X input. So this is the fireplace coefficient times 1 fireplace, the Crawford coefficient times 1 because it was in the Crawford neighborhood, the North Ames coefficient times 0 because it wasn't in that neighborhood. That's the case for the rest of these too. The overall quality rank coefficient times the overall quality rank, and the living area coefficient times the square root of living area. So that's ultimately what we're going to be doing in this worksheet, is multiplying each of these coefficients by the input values. So if you want to put coefficient times input, you can do that here, and we can use our format painter to make that look consistent if you want. Okay, now the next thing is to just do the multiplication. So it's just equals coefficient times input value. Okay, so once we get it done right for 1, we can just drag this formula down to fill those values. And the reason why you see more decimal places here is because there's actually a lot more decimal places here. We've just reduced them. So we can reduce these two just to make sure that it looks nice and neat and consistent. So now the last thing that we need to do is we need to add together all of these multipliers. So this was multiplied by this multiplied by this, and now we sum them all together. So if you look back at the model equation, we do each of these multiplications inside of these parentheses, and then we add the products of those all together. So that's essentially what we're doing in this step. So we can use our sum formula to add this column of multipliers together. So it equals sum, open parentheses, we would select these values we want to add together. Okay, and that is our prediction. So I'm going to merge these cells right here together just so I can have room to see, to put, this is the predicted cube root of sale price. Okay, and this is for test case 1. So if we want to give this table right here a title, okay, we can merge these together, and this is test case 1. Assessment or prediction. Assessment. Okay, and then we can format paint our other title to make sure that those are consistent. Okay, so the next thing that we need to do is we need to convert this prediction to not from cube root of sale price to the actual sale price. So we're just going to put predicted sale price. Goodness, can't type. Sale price here in dollars. Okay, so again, we took the cube root, we raised every sale price value here to the value of 1/3 to get the cube root. So in order to convert it from the cube root back to dollars, we need to cube it. We need to raise it to the power of 3 instead of 1/3. So we would take this cube rooted value of sale price here and raise it to the power of 3. And then we can format this as dollars. We'll reduce the decimal places, and we should see our predicted value there. Okay, so that's again our cube root of sale price value and our predicted sale price. Now, if you see that like a series of hashtags, it just means that the cell is not wide enough to display the full data. So you can just either widen the cell, reduce the decimal places, just make sure it's nice and neatly formatted. Okay, now if we want to compare this to the actual, right, the actual cube root of sale price for this observation, okay, we can merge that together, merge this together because we'll do the conversion as well. So the actual cube root of sale price is up here, right? And the actual sale price is here. So we can equals this cube root of sale price value here, okay? And then we can do actual sale price in dollars, and you can grab that value from here, or you can also take this value here and raise it to the power of 3, so cube it to get it back into that original value. Okay, the differences that we just see here are a rounding error from the original data. We can, in order to, I don't know why that's formatted as a dollar sign, but to get the actual cube root value, I don't know if it's in this. No, it's just from the slides. So it is, but $4 difference, again, that's just due to a rounding issue with this cube root of value when it was copied over. So not a big deal. It's still going to be close to 222. We can also ignore this error right here. Okay, so if we want to calculate the difference, okay, then we would do actual minus predicted, and we would see that, I think in the slides it was a $222 difference, $217 difference here. Again, that's just due to this being rounded to 2 decimal places instead of the full number of decimal places that the sale price actually was. So actually, if we wanted to change that, we could take this value and raise it to the power of 1/3, and then that would make sure it was consistent with or close to what we see in that original, so 221. In any case, you should be within, you know, $4 or $5 of what you see on that slide. Okay, then we can clean this table output up if you want. Just make it look nice, and then we can highlight the difference here in that same green color, just so we can see kind of how off we were in our prediction. Now, when you want to do this for the other test cases, okay, because you're going to get these same test cases, or similar test cases for your homework subsets, you'll take this, you can paste it over here if you need to expand that, and then all you should really need to do, okay, is highlight this, the inputs here, the coefficients remain the same, copy, transpose, paste them here, okay, you should see those update, and then we do want to make sure, okay, that's summing I-12 through I-19. Okay, so we're getting a predicted value of 104. The actual cube root of sale price, okay, equals right here. Okay, again, it's just a bit of a rounding error. You can just leave it, it's going to be very, very close. Or you can, if you want to do the cube root of these values to make sure that they all match up. That's fine too. Okay, so we can see our difference here being that $9,000 difference, the same one that we saw in the slides. Okay, and again, you can ignore this error. It's just letting you know it's not consistent with the other ones. Okay, so this is actually test case 2. Okay, we'll copy this, paste it here, open that up. Okay, can open those up a little bit. And then for test case 3, make sure, again, all we have to do is copy these inputs here, right click, and then when we come over here, we'll right click to transpose paste so that it pastes downward in the column. Okay, and then the thing that we will need to correct is this reference to the cube root of sale price, which is right here. So you just reference this actual value here. Okay, and then you should get that prediction difference that looks very similar to the ones that are in the lab slides. Okay, and then, so those are your 3 test case predictions. Okay, we can see how well the model is performing. Now, again, when we do this in practice, we generally, a common train and test scenario is we would train the data on 80% of the sample, and then we'd test it on the 20% of the sample, like an 80-20 split. And then we would measure how well our predictions were, or how accurate our predictions were across that 20% of the test cases. So if we had 1,000 observations, we'd use 800 of them to train the data, and we'd test it on 200 of the observations. We could also do something called cross-validation, but ultimately this is to just ensure that we haven't built a model that fits the sample data really well, but doesn't generalize to new observations that it's never seen before. So that's your kind of wrap up for making a prediction. I know there's a lot of steps involved in this, but you have these references here to make sure that you're on the right track. This is the same process that you'll go through when you do this for your homework subset.